All right, recorded is rolling. It is Monday, December 12th. We did start the midterm review back on Friday, so we're going to keep doing that. You guys do have rotational dynamics quizzes back in your folder. You guys are really awesome on that. You guys can see here, but I just want that back at some point then. That is there. If you want to do corrections, that's an opportunity too. All right, got, where's, up here. Aha, got Spirit Week. See some holiday hats going on here. Right, there's next few days coming up. It's like tomorrow is Ugly Sweater Day. Oh yeah. And here's the midterm schedule again. Remember, your very first midterm is this Friday. That's your 7th period class. And then since you guys are first period right now, that'll be exactly 1 week from now. You guys come in and be taking this midterm. You guys remember this midterm is going to be half multiple. There's going to be 50 multiple choice questions. They're just conceptual questions. We'll cover those later this week. And there's going to be 10 questions that are 5 points each that are you have to break out some formulas, apply some problem solving. Okay, so switch my screen over here and we'll pick up the review where we left off last week. All right. Remember, remember Friday was a short day. I think felt caught by surprise. Right, so we were approximately here. This is the dynamic section. So by APs, but this is unit 2. And this is a really classic question here, just block sitting on an incline. Okay. Now, equilibrium, you guys know, means that there's no net force and also no acceleration. I mean, one implies the other. Okay. That might mean at rest or might mean moving at constant velocity. Right? It could be either of those. Okay. You guys should definitely be able to, by this point in the year, draw the free body diagram for that. By the way, how many forces should that block have on it? 3. What's one of them? Okay, yeah, I'm hearing all. Yeah, so it's got a weight. I mean, if it didn't have a weight, then it wouldn't have the other 2. Okay. Now you can break the weight into components. Remember, AP always emphasizes this idea of, like, they say not components. Don't draw the components. Right. But you can either dash them. Usually they'll let you do that, or you can just imagine there some version there. There's a normal force and there's a friction force. Right. The normal force should just be mg cosine theta. So there's nothing crazy going on. Friction force should be mg sine theta in the case of equilibrium. Okay. Okay. So that's good. All right. Elevator physics. So this elevator, 3 different frames. It's the same weight. You guys see, it's the same weight elevator. All 3 of these. I put an apple on a bathroom scale in there for you guys. That top-down view of the scale. What's going on? Okay. Now, this elevator might be accelerating downward, or not accelerating, or accelerating upward. Okay. So accelerating downward would mean that the tension force is not as much as the weight. Okay. It might be moving down faster and faster, or it might be moving up but slowing to a stop. Right. It could be either of those. Okay. Now, the middle one, equilibrium. If you just saw the free body diagram, would you know whether that elevator was at rest or not? Just based on the free body diagram? No, it'd be ambiguous. It might be at rest, or it might be moving up at constant velocity, or it might be moving down at constant velocity. It might be moving fast, might be moving slow. You have no idea. Okay. All you know is that the tension force up is equal to the weight down. Okay. And if it's accelerating upward, that's because there's a net force upward, right? Because it's being pulled up more than it's being pulled down. Okay. You guys go with this? Elevator physics, right? And these equations down the bottom, these expressions, there's a good chance that you'll actually be asked this on the AP exam in May, but you'd be expected to derive that from scratch. You have to say, okay, well, go back to Newton's second law of motion. The net force is the difference between those 2 forces. Oh, Ryan, I got you set up in the back with John and Leah. Leah, fix this real fast. All right, here we go. Right. Atwoods. Right, so here's a classic Atwood, double elevator Atwood. There are really 2 external forces, which are the weights, right? Care about M1G and M2G. Now, the tension force is an internal force, and these boxes off to the right, it's not. All these statements are true, right? So the top box is just plain Newton's second law of motion. Okay? The second box specifically applies to this setup, right? Newton's second law of motion applied to this. Okay? And those last 2 boxes there, are honed in on each mass individually. So this third box is from the point of view of M1, this last box from the point of view of M2. Right? Of course, the tension is the same, right? There's one tension in that string, right? You guys can navigate all that. Okay. Really good chance you're going to get some Atwood questions on the exam in May. Be able to navigate that. There's a whole labs about this, right? Here's an example of a modified Atwood. The one we did in class was actually even simpler than this because I had you guys prop a Hot Wheel car underneath this one here, which pretty well got rid of that friction. But if you include the friction, then that's how you would do that. Okay, guys go there. Any questions so far? Anything? Car brakes to a stop. There's a few slides that have this exact same title, just different points of view. This one maybe wants to get at what's the free body diagram. You guys could come up with this free body diagram, right? Car's moving to the right, but there are no forces to the right. There's a force to the left. Right? That's what's breaking it. Right? It's the net force. Right? Could you guys do this derivation right here and get the acceleration cars coefficient of friction times the gravity field of the planet? Okay. Starting from Newton's second law of motion. Boom, boom, boom. Just do some substitutions. You guys can figure that out, right? Okay. Good things to know. Okay. What if the car is turning and it's on a flat track? Okay. Now, if it was on a banked track, it's probably easier to get it to turn. Maybe the horizontal component of the normal force is acting as a centripetal force, right? But that's not what we have here. What we have here is if the track is flat, what is the force that's allowing it to turn? Yeah, and what force is acting as a centripetal force? It's not the weight, it's not the normal force, it's not a tension. Friction. Friction. See, if there's no friction, you couldn't turn like this, right? You guys remember that Nigel School Bus clip where they went inside the textbook where there was a frictionless baseball field? Remember that? Right? You can never make this turn on that field, right? Okay. So yeah, from above it would look like this, but from behind it would look like this. Okay. You guys can figure that out, right? Okay. And you don't see all three forces on the left because two of them are pointing into and out of the page, right? Okay. Vertical loop, right? So you have maybe a ball on a string and you're flying it around a vertical loop. Okay. Guys, where is the tension the greatest? At the top or at the bottom? Yeah, bottom. The greatest tension in the strings at the bottom. Where is the ball moving the fastest? Top or the bottom? Bottom, right? So this is a free body diagram point of view. One of your progress check questions was, what is the tension in the bottom compared to the tension at the top? And they asked it sort of like I think they gave it like an inequality, like it's at least this big, blah, blah, blah. But then remember I asked you guys as a quiz question exactly what's the tension bottom compared to the top, right? I think the only reason they didn't ask you exactly because it took some time to sit there and solve, right? It took more like 2 minutes to solve, okay? But another classic question is like, how fast do you have to get this thing going to make sure it gets around the top? You guys remember this cup right here on a string? I filled this thing with some water, right? And threw it around in a vertical loop. Right, and the water didn't fall out because it was going fast enough. There was like a minimum speed, right? And at that point where it's the minimum speed to get around, what would the tension approach right at the top? Maybe like zero. The tension would go to zero pretty much, right? If you just get the minimum speed to get it going around, right? Right. So here's net force at the top would be the sum of those two. But if you let the tension go to zero, and the net force is centripetal force. So the centripetal force is only provided by the weight. You said, boom, it has to go at least that fast to get around the top. Right? If it's going any slower, it's going to be some slack in the string. It's not going to make a circle. Right? Water's going to fall out of the cup. Okay. I think this some version of this scenario is going to come up later for conservation of energy, or it could, right? You say like, well, how fast is it going to the bottom compared to the top? Right? That could be a good conservation of energy question. Pendulums. So, well, that's what the free body diagram would look like. There'd be two forces on that pendulum, right? It's weight pulling down and the tension force, right? Now, if you add those tip to tail, that's what the dash vector is about, like tip to tail vector connection. Okay, you get the net force, which is going to be tangent to this circle motion, right? So it's going to make it accelerate. Hey, that picture, actually, either one of those. Do you know if the that apple's kind of going up to the left or down to the right? Can you tell its direction of motion? No, its direction of motion, it's ambiguous, right? Because it would have the exact same free body diagram, regardless of its direction of motion, right? If it's kind of on the upswing or kind of on the downswing, it's the exact same free body diagram, exact same acceleration, right? Maybe different velocity though. Right? Could be either one of those. A conical pendulum. So these are classic questions here. So I'm thinking two forces on this apple, two true forces. Okay? Maybe it's weight and the tension. Those are the two true forces, right? It's weight down and the tension force up to the left. Right? Okay. Now, again, if you have those tip to tail, you get the net force, and the net force is horizontal, and that's the centripetal force. It's acting as a centripetal force, okay, because it's just holding it in a circle, right? Right. So that the ball is just going to move on this dash line green path, right? You guys see that? Right. And the vertical components of the force is sum to zero, right? It's not going up or down, right? And the horizontal components of the force, well, that is the net force, right? Hey, is that apple in true equilibrium? No, because there's a net force on it, right? There's a net force, right? Anything that's moving in a circle cannot be in true static equilibrium because it's changing its direction, right? So there's a net force on it. Oh, okay. Here's a pretty straightforward one. Just take something from a spring scale. Right? You could say something like this: the up force equals the down force, blah blah. Expression like that. You guys remember that day I had you guys do like 10 mini labs with the spring scales? Right? And this was one of them that I keep coming back and talking about. So can you guys see the three forces on this apple right here? Three forces. Okay, what's one of them? Gravity. Yeah, the weight acting down, and then each of the spring scales. Right? No, the total force has to sum to zero, right? Okay. Now, you could do like tip to tail for all three, and they would just like make a triangle shape. Okay. Or the way I always do it in class is to break them into components. Right? You guys see those two blue components have to cancel out. Right? That's what the stop line says. Right? You guys see that the green components, these two dash ones up, balance with the weight down. That's what the green one says. Right? You guys do that. And what happens if you? Okay, that looks kind of like a Y shape, right? Like a Y. What if you pull those spring scales out to make this closer to a T shape? Right? What's going to happen to the green components? Nothing, right? Like if the apple weighs 10 newtons, then they'll be at 5 and 5, right? But what's going to happen to the blue dash components? Ooh, those are going to get bigger, right? They'll still cancel each other out. And what happens to the reading on the spring scales? They step up, 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 right? In fact, if you had something pretty close to a T, what would the spring scale readings be? It's like enormous, right? Just head towards infinity, wouldn't it? Right? 10 towards infinity, right? Can't make a perfect T. Oh, yeah.
So x component for stretching it.
Yeah, okay, so the spring scale reading is like the Pythagorean theorem resultant of the dashed green and the dashed blue. Okay? The dashed green, I mean, if it's all symmetrical, like I drew it here, is each dashed green one's going to be half of the weight because it adds up to the weight, right? And then from there, you can just do it based on geometry. Like if you know what this angle is, you just bring in all your trigonometry, right? Like the physical angles. Yeah. So, yeah, if you do this green dash squared plus this blue dash squared, you'll get the spring force squared.
The blue dash is f of x, so f of x will get bigger, right? And the stretch.
Right. Yeah, bigger to the right, and this one gets bigger to the left, so they still zero out. Right. Right, and Fy stays the same. Yeah, yeah, because it just has to balance out the weight. There you go. All right. All right, so some rotational kinematic stuff. AP actually puts this in unit 7. We touched on this back in unit 3 because we were doing somewhere like centripetal force stuff. So okay, well, I think it's relevant back then. Right. So can you guys translate back and forth between angular motion and linear motion? Okay. Now this depends on like where you have something. Remember, like you guys remember put like 3 Roosevelts on a turntable? If you put one right at the middle, then it doesn't really move anywhere. Okay. And then the further out you put it, right, the larger its radial distance from the center. So like all these are having the same turns per time. Like if it does like 1 revolution per second, they all get the same. Right. But the further out it is, like the further distance it goes in terms of meters. Right. Right. Is that true? Okay. It's even possible you might get a trick question that says something about displacement. Right. So suppose it makes exactly 1 revolution. What is the displacement? 0, right? 0 displacement. Right? But the distance would be 2 pi r. Right. So definition difference there. Right. Velocity and acceleration work the same way. This is tangential velocity or tangential acceleration. Right. So is centripetal acceleration anywhere on here? I haven't written anywhere. There's nothing that says anything about centrifugal acceleration. So I have tangential acceleration, like spinning up in a straight line at one instant. Angular acceleration could be the turntable, like speeding up or slowing down, right? Radians per second squared. Okay. Now, if you wanted centrifugal acceleration, that could be like that could be like v squared divided by r, right? You could do that, or omega squared times r. You could do that too. Right. Rotational kinematic formulas. So these are just your right. Okay, so you guys know those, right? Because we use those. Okay. Like how far is it turn in radians? Hey, that's kind of analogous to how far is it moved in meters, right? X equals v naught t plus half at squared. Just pop in the rotational equivalents. Boom, boom, boom. Okay. Here's the same thing, just looks a little cleaner. You guys can navigate those. Okay, question about those. Okay. It's like how fast is it rotating? Well, how fast was it rotating? What's the rate? It's changing its rotation speed, right? And how much time, right? For example, right? How far is it rotated? And so you have to use radians, right? Radians per second squared. Okay. A turntable slows to a stop. Ooh, got some graph opportunities. Oh, turntable slows to a stop. What do those three graphs look like? Okay. So how far is it turning as a function of time? How fast is it turning as a function of time? And the rate that it's slowing down as a function of time. Okay. Let's assume uniform acceleration. Okay, like pretty much always do in this class. Maybe a couple exceptions. Okay. What are you guys thinking omega versus t would look like that? Okay. Ooh, does this look a lot like a car braking to a stop in a linear sense? So this is just turning, right? And I started with that one because that's an information-rich graph, right? The slope represents the angular acceleration, which looks like it's negative and constant. And the area under omega versus t tells you how far it's turned. Okay. You guys see if you subdivide that into like say 1, 2, 3 seconds, it'll go a long way in the first second, then not as much, and then not as much. Okay, but it's always moving forward. It's just doing it slower and slower. Okay, so those are the three graphs right there. Right, you guys could draw those from scratch. Okay, here's I guess fun trivia. Right, so different technologies. Okay, fun trivia, more fun trivia. Foucault pendulum. Okay. So if you have a pendulum swinging, especially closer to the poles, right? The Earth might turn underneath it, but it's just going in a straight line. So from the surface of the Earth, it looks like it's rotating, but really it's just going straight. Okay. Right, more fun trivia, not going to show up on AP exam, but good to know. Coriolis effect. Okay. So the Earth is spinning, but things want to move, and according to Newton's first law of motion, so from the surface of Earth, it looks like, hey, why are we missing our target? That's if you're in the northern hemisphere, it's going to do that. But just like that. Okay. L stands for low pressure, meteorology, hurricanes. You can explain with this. All right, so back to classic physics. Centripetal force. Remember, you guys did a lab on this. Okay. This is the PVC pipe and the Play-Doh canisters and string. I mean, I always reference this one, right? Okay. Guys, remember what is the expression for centripetal force? And v squared over r. Right. Now, on the AP equation bank that you're allowed to reference, they don't actually print this one, but they do print this one underneath it. It says the v squared over r is centripetal acceleration. So they actually give you this one, although you say, okay, well, times mass to get the force, right? F equals ma. Right. These are Newton's second law of motion away from each other. Okay. Right. That's good. O'Neill cylinder. Right. So whenever you have like either a turntable or big rotating solid object, it's usually more convenient to solve whatever question you're asked in terms of rotational mechanics. So yeah, you could solve in terms of like v, but it's usually easier to resort to omega, like how fast the whole thing rotating in radians per second. Okay. So you can ask a question like this guy right here, if you want him to close his eyes and think that he's on Earth, well, he has to feel Earth gravity. Okay. So maybe how fast do you have to get this thing rotating? Well, it depends. It's radial size, right? So it's going to come down to something like this. Okay, omega squared times r. So the sort of linear equivalence where centripetal force was mv squared divided by r, and centripetal acceleration was v squared divided by r. Right? If it's rotating, multiplied by r. So how about this? Like this guy climbing this ladder, he's right at the center. What artificial gravity field does he feel? Like 0, because you can multiply by 0 here, right? If you let go of the ladder right at the middle, he just kind of float off into space. Right? And if he's halfway down the ladder, I bet he feels half of Earth gravity, and then down at the base he feels all of Earth gravity, because however far he's down the ladder from the middle. It's the artificial gravity field is proportional to that distance. Right? The whole thing's all turning together, right? Okay. Kepler's laws. So Kepler says focus really close on the motion of planets. They actually follow elliptical orbits around this sun. There's this fun law about equal areas and equal times. Okay? And Isaac Newton actually uses to help establish physics and come up with laws of motion, universal gravitation. Okay? Kepler, this third law says the square of the time period is proportional to the cube of the average distance from the star. Okay? And it's consistent with, here, if you update it with Newton's laws of motion, you get this expression right here. Okay. Is AP going to ask about that? Probably not, or if they do, they would probably feed you a lot of the information so that you could solve it, but bunch up there. Inverse square law. So classic example could be like intensity of light. That's what I is in this case, like intensity of light. Right? All the universal gravitation, same idea. Okay. So if you back it like 3 times as far away from some object, you get like 1/9 of the effect. So it's like 1 over the distance squared. Okay. And now that's a proportionality, right? So I'm saying that's not the full equation, that's just part of the equation. We're just focus on one relationship there. And so universal gravitation, it's an example of this inverse square law. Okay. GMM over R squared. Okay. Hopefully this is one of these that you guys have committed to memory just because you've used it plenty of times, right? You had to use that in so many derivations. Like every time you derive orbital velocity, orbital speed, right? Good chance you have to do that in the exam. Right? You start with this is equal to centripetal force and then blah, 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 go from there. Okay. What if 2 objects, say you have 2 asteroids and there's some distance between them, right? And then that distance gets cut in half as they gravitate toward each other. Because if you have half the distance, what happens to the force? It's not twice as much, it's 4 times. Yeah, 4 times as much, right? It's stronger, and then that square, so inverse square relationship, right? Oh, orbital speed. There you go. Okay. Really good chance you'll have to derive this in May. So you say, well, the centripetal force is provided by only the gravity force. So you have like a satellite orbiting planet, something, right? So here's centripetal force. Here's universal gravitation. You can solve for the V, right? Orbital speed, and you always get that expression right there, right? That's a good one to know, right? Have in your back pocket. Although if you just pull it out from scratch, you probably lose some points, but you might have to derive this first and then say, there you go. Good thing to know. And this actually doesn't belong in this section, but it kind of goes hand in hand with it. Escape speed. I don't know if I've ever seen AP ask a question about this, but yeah, I mean, it's really similar looking at expression, right? There's just slip a 2 underneath there. Right? So take your orbital speed, multiply by square root of 2, and get how fast you have to go to break the gravity and fly away forever. It's conservation of energy concept, really. Right. Here's all these ideas thrown together, right? So got the stick figure guy. Looks like the animation has been dispersed. That's the gravity field he feels at the surface of the planet. Right? Orbital speed for the satellite, escape speed for its rocket. Boom, boom, boom. Did I show you guys that this actually I stole this from Paul Hewitt. Did I show you guys the Paul Hewitt video on this? Yeah, eggshell planet. Okay. So it's just an eggshell, giant empty planet like a giant basketball. Okay. The forces cancel out, so there's gravity-free interior. Okay. Now that may seem like okay, it's an abstract exercise. We're going to find an eggshell planet. But it's actually useful to figure out things like what if you tunneled into a regular planet? You're like halfway down to the center of the planet. Okay. What you can say is that everything above you in elevation just cancels out. So it's as if none of that exists. And because it's like a series of shells, right? It just cancels out. Right? And then everything is just like a tiny planet beneath you in elevation. Okay? You can just treat it like that. Okay? Take it to the center. In which case you experience 0 gravity. Right? Tides. I don't think AP asked about this either, but good to know that right. There's say like the Earth and the Moon, right? There's one surface that's closer to the Moon, one surface that's further away, so they experience different gravity forces. Right? Lagrange points. Again, I don't think AP asked about this, but I guess learned about it. Right? About a year ago, NASA sent up James Webb Space Telescope. They have it orbiting this L2 point. Right? These are points of like gravitational equilibrium, sort of. Forms of mechanical energy. So like especially know the yellow ones, and then if you want to go a couple extra steps, focus on the green ones. So work is a transfer of energy, force times distance. Right? That could be weight times height. If you apply a force to carry its weight, lift it up some distance, which leads you straight to the second one. Right? If you lift something, put it on the shelf, it has this potential energy. Oh, that's weight times height right there. Right? These two really go hand in hand, right? You know one, you kind of figure out the other. Okay. We skip down to here, spring potential energy. If you compress or stretch a spring, 1/2 kx squared, energy stored in the spring. Now force is equal to kx, but that force changes the more you compress or stretch it because, right? And so if you accumulate the energy, right, it's 1/2 kx squared. Right? Kinetic energy, energy in motion, anything that's in motion, 1/2 mv squared. Okay. All right. How about rotational kinetic? All right, so if something's like rotating, 1/2 I omega squared. Actually, I think this is a little bit updated from. Well, yeah. Right. So then go back to this first green line. Potential energy from a universal point of view, negative GMM over R. Now, if the radial size is not very big compared to like mass pulling on it, it's like from the top of Mount Everest to sea level is hardly anything compared to the radius of Earth. Okay. Then you can show that it simplifies to MGH, right? Which is really probably all that you guys care about for this class, just MGH for potential energy. Right? But if you're sending a rocket to the moon, you have to use the universal form of it. Okay. That's good. Oh, there you go. There's work is force times distance. Now it's a dot product, meaning you only multiply the parallel components together. So break these guys into components. Okay. Now, I think it's easier to associate that cosine with being like some component of one of these. So I gave you guys an example for each one. Here's the cosine component of the distance. Here's a cosine component of the force. Okay, so however you like to think of it. Okay. Okay. Guys good there? Ooh, work. That's the area under force times distance. So an application of this might be like, suppose there's our rocket ship and it's it's just coasting through space at some speed, and then it blasts its engines, and they tell you how far it does that for, not the amount of time. Guys, if they said force versus time, what is the area under force versus time? Impulse, which is a change in momentum, right? So be careful about that. If they say they blast the rocket for blast the engines for 3 seconds, then you would not use this exactly. You would say, okay, well, I'm going to set an impulse equation, right? But if they say you blast the rockets for like 100 meters, that's this right here, right? So, okay, blast it. So much force for like so many meters. Like, that'll tell you the change in energy. And if it's a rocket in deep space, that's going to all translate into what kind of energy? There's no gravity nearby, so it can't be potential. It must be kinetic. So it's going to like speed up the rocket. Okay. And then the final energy could be 1/2 mv squared. You can solve for v and figure out how fast the rocket going after the rocket blast, right? If it's been blasted for 100 meters. Okay. So it could be like 1/2 mv naught squared plus this green brick is equal to 1/2 mv final squared. Okay. You can just solve for stuff. Okay. Closed system, open system for energy. So if it's closed system, that's your classic energy is conserved, right? And then you might have different kinds of energy. We'll go do some examples in the next few slides. If it's an open system, how's that going to differ? You could have work done on or by the system. That's what the plus or minus is about, right? Okay. Okay. So I just gave you guys an example for this. Right? So the rocket's in deep space, it has some 1/2 mv initial squared. Plus you blast those engines some force times distance. Okay. And then you end up with some 1/2 mv final squared, and then solve for that. You guys can do that. Okay. Real fundamental example here. Galileo drops the ball, leaning tower. Closed system. Well, what would be in the closed system? That could be a good AP question. What would be in the closed system? The ball and the Earth. Yeah, ball Earth system. Right? So that kind of energy at the top, that kind of energy at the bottom. It's real straightforward. Right? And that's always the answer to that, right? You guys have probably seen this at least a dozen times in this class, probably maybe 2 dozen times at least, right? I mean, this shows up again and again. Right? Now, if he chucks it down, it'd be v naught squared plus 2gh, and then the square root of all that. But if he just drops it, it's always root 2gh. Okay. I like this one a lot because it combines a lot of those different forms. Right? So we're going to compress this spring, then pow, and it flies off. Let's say there's no friction. Okay. So what was the energy to start with? what kind of energy? Spring potential, right? Spring potential. So 1/2 kx squared. That's right here, right? It's all spring loaded, ready to go. Now, pow, and it takes off. There's a mix of energy up here. There's what and what?
Potential and kinetic.
There you go. Gravitational potential and kinetic. Right, so that would look like that, right? And then if you knew a number of those things, you could just solve for whatever you wanted to solve for, right? Ooh, okay, this one's kind of complex, but yeah, I think you guys should be able to do this, right? So this is like a two-parter. So how high does the roller coaster have to be to make it around the loop? Right? And there's a classic answer to this. It's a really classic physics question. Does anybody remember what the answer is? Happen to? It's always like 2.5 times the radial size. Great. And how do you get that? Well, this better have some speed to get around the top here. Otherwise, it's going to fall off the track. What is that speed? Oh, well, we did that earlier in this presentation. It's the minimum speed is square root GR. You guys remember that? I'm going to sort of pause it a step for that because it's easier for the substitution. You can say V minimum is square root GR. Right? That's back to this cup full of water, right? Yeah.
Wait, why is the normal force also?
Okay, because we're looking for the minimum speed. And at the minimum, then the centripetal force is only provided by its weight. So like the force pushing down from the track would approach zero. Yeah. Okay. All right. We good there. All right. Now we're gonna hold on to that idea. That's from dynamics. That's from last section. Okay. Then switch over here. Conservation of energy. What kind of energy at the top? Potential energy, MGH. Now, if we're treating this as height zero down here, then by the time it gets to here, it has some mg2r. 2r would be the height plus some 1/2 mv squared, where this would be the v. Right. So that's like that going on right there, right? Okay. You guys could come up with that. Okay. Then where that v squared is, I'm just going to replace it with a gr. Boom. Right. And then go on and do some algebra, and that's always the answer. Right. The mass cancels out, so it doesn't matter if it's loaded with passengers or not. Right? The G also cancels out. So if you took this whole system to Mars, you get the exact same answer. Pendulum speed. I think your textbook question version was like some adventurous archaeologist swinging on the vine. You guys remember this one? Okay. There's a few good questions you could ask about this. This is just one of them. It's like how fast you go on the bottom. Right? So you could have, okay. You guys got to do some geometry for this, possibly, right? You might have to do some geometry. Right? I can see AP making you do all these steps, right? If you know L and theta, you say that's L cosine theta, and this is L minus that, right? Right. Could factor in L and L if you wanted to, right? You guys could do all that. Right? You guys can do some geometry, right? It's just some geometry, right? Right. Now let's kick over to the conservation of energy physics, right? Which could look like this. Right? Now the gray part is like if you push off, you get the gray part. Right? If you go from rest, the gray part doesn't exist, right? Right? Right. And then you can solve for V at the bottom. Now V at the bottom is just square root 2GH. Right? As long as you start from rest. Right? If you kick off, you get this gray part again. Right? Right? And the H is this whole expression right here. Okay. Just kind of square root 2GH, right? Okay. Guys good? Car brakes to a stop. You guys have seen this before in this presentation, right? But now we're different point of view. Now we're doing an energy point of view, right? I mean, there's the free body diagram for it, blah, 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 right? So I'm going to treat this as an open system, maybe consisting of only the car. So just a car, open system. Right? There's an open system right there. Boom. Right? The work done by friction would take energy out of that system, wouldn't it? Okay? So the car starts off with all kinetic energy in motion. It ends up with no energy because it's at a stop, hasn't gone up any hills. Right? And lost force times distance due to friction. Okay? That friction force, though, is related to the normal force by a coefficient of friction. And that normal force is equivalent to the weight as long as it's a flat road, right? So you do a series of substitutions right there, right? There's a few substitutions. Okay? And the distance the car goes, slides to a stop, is always equal to this expression. Now, if I just pick out some relevant parts there, I could come up with a proportionality and say the distance the car slides to stop is proportional to the square of the initial speed of the car. Right? We've done this many times in this class, right? I keep asking you guys, like, what if you triple the speed of the car? What happens to your braking distance? It's 9 times, right? 9 times the braking distance. You guys remember this, right? All right, so Atwood questions are also good opportunities for conservation of energy. So I just picked one and went with this. There, that's better. All right, so say you have an open system because I could have a frictional force. So I'm gonna, okay, so got an open system, okay? And the initial energy is all provided by the fact that this heavy one can fall. Right? The heavy one can fall, so we're providing the impetus for this thing to move. Okay, so that's going to be everything in green. Okay, I'm going to subtract off force of friction times distance, which you guys see the distance and the height change is the same thing, right? I think this was one of your textbook questions or something very similar to it. Okay. Now the energy that you end up with over in blue, okay? Well, I'm thinking 4 different things. Right? Each of these masses is going to have a speed. So boom, 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 there's 3 kinetic energies. And also, this little guy has been lifted. So some energy went into lifting it, right? Wouldn't that be true? So boom turns into boom. Okay. Just like that. You guys can figure this out. Pulley system. Okay. You guys did a whole lab on this, right? So energy is conserved. That's right. It's the principle behind how this is going to work. Right? Work in equals work out. Right? If you have a 100% efficient system anyway. Right? So force times distance on the side of the spring scale is equal to force times distance on the side of the weight that you're lifting. Right? Okay. And the ideal mechanical advantage is the ratio of the distances, which in this case would be 3 to 1, or just based on the geometry. Okay. You guys see this movable pulley has 1, 2, 3 strings going up. So it's like the weight's been split 3 ways. So if you're on the side of the spring scale, you feel 3 times as strong. Okay, so whatever force you input, you got to take 3 times the output force. Okay. Now, in reality, okay, you guys saw this in your lab too. There might be little frictional forces or losses one way or another. Okay. So the actual mechanical advantage is the ratio of the forces, which is usually a little bit less, might be like 2.5 to 1 or something like that. I guess you do a 3 to 1 mechanical advantage split system. Now, I could have had you guys break up something else. So I got a couple of slides for alternatives. You guys could have used wheel and axle to create a 3 to 1. That mechanical advantage is just the ratio of the size of the wheels. Right. So, right. And then actual mechanical advantage is the same idea as the ratio of the forces, which might be a little bit less because they're frictional losses. Yeah. Right. An incline also has a mechanical advantage. I don't think I ever explicitly covered this with you guys either, but if you have a small incline, then you can push up a very heavy crate that you wouldn't normally be able to lift, right? So you get a mechanical advantage that way, right? Yeah, if there's no frictional losses, then just be this, like how far did you push it, how high did you lift it, and just take the ratio of those two. Mechanical advantage that way. Okay. So just showed you guys 3 slides on mechanical advantage. One of them you guys did in lab, so really familiar with. Okay. Here's a full classic list of simple machines you can have. Momentum. You guys know it's mass times velocity. You guys know that it's conserved. You guys know it's a vector value, right? And it's involved in collision physics, right? You guys know all those things. Closed system, boom. Open system, boom. Right? Impulse. You guys know there's a change in momentum, so that would follow, right? Closed system, open system. Now this is force times time, right? Force times time. Should say average force times time, right? So here's just general conservation of momentum. 2 things collide head on. Notice we're keeping everything just along one axis, right? Which AP will do too. I don't think they really ask 2-dimensional collision questions, right? So like that. Right? Just general conservation of momentum. Okay. Now there's some you might have them collide and stick together. That's perfectly inelastic. AP really likes this kind of question. They ask this one more often than any other kind. Okay, so really good chance you'll see this in particular. Okay. Can you guys just do that? Just say, well, you have common final velocity post collision. Okay, come up with that, right? Okay. Now elastic. Is my computer frozen? No. Okay, hang on. Right here. All right, gotta reset this thing. Okay, I think we're back here. All right, so perfectly elastic, that's like perfectly bouncy, like Newton's cradle. The math gets really crazy. AP would not expect you to be able to figure this out in a short amount of time. If they ask any question about this, it's usually something really straightforward, like one mass knocks into another mass that's equal to it and was at rest. So you can just imagine Newton's cradle, like bam, just transfers all its energy to the other, something like that. Right? Okay. Coefficient restitution. AP never asked about this, but I like this. It's just how can you quantify how bouncy is something? Okay, so I had you guys do this lab. Okay, coefficient restitution. If you bounce off the floor, you can do a modified version of this. Okay. I think you should be able to figure this out. I mean, I guess they could ask this if they had the information. So here's the setup. Okay. You guys can figure that out. Impulse. Okay, so change in momentum, and this is force versus time, right? Now, but guaranteed you will get this question on the AP exam. Okay, so force versus time graph, look for that. This could be you're in a rocket going at some speed, and they blast the engines, and they tell you how much time for. So they say you blast the engines for like 8 seconds. You say, okay, I know the blast force from thrusters. I know how much time. So I can tell you what the impulse is, which would be the change in momentum. Okay, and you could set up an equation that looks like that right there. If you hit a bat with a ball, you might get a graph where it's more like a triangle shape, right? You just find the area under the curve that will tell you the impulse. Okay. So you guys can do this. Ooh, ballistic pendulum. So here's another one of these complex questions. It's like a two-parter. And the question is usually what's the firing speed of the bullet? And you can see like how far does it swing up to. So conservation of energy, you just backwards chronologically. You say, well, if I know how far the pendulum swung up to, I can figure out how fast the post-collision velocity was. Oh, no, look, square root GGH. Right? I've seen it so many times before. And you say, well, what happened before that led up to that point? Well, there was a collision between the bullet and the block. So there's your conservation of energy, momentum, conservation momentum, because there's a collision involved. It's perfectly inelastic. Field substitution right there. And there you go. There's the firing speed of the bullet. And it's always that right there. Here's your answer. Yeah. As long as the bullet embeds in the block. Yeah. I've seen the question asked too, like, what if the bullet like passes through the block? It's probably not going to be thrown that way, but I guess you guys can feel bad if you're given that. But this is if it embeds in the block. 2D collision. You just say the momentum is conserved along each axis, the x-axis, the y-axis. Again, I've never seen AP ask that question, so I don't think they will. Center of mass. AP asks center mass questions, but it's not really formulaic. It's more like it's more like, say if you have a bunch of kids on a frozen lake and they're like throwing a snowball back and forth, right? Something like that. And you say, oh, well, the center mass like wouldn't move. Or if they were already sliding, then it would just, the center mass would just keep doing what it's doing. Or if there's like someone walking along a plank inside a lake or something, right? The center mass just wants to stay inside the system unless there's like an outside force acting on it, right? So that's more like an AP direction center mass. But there you go. There's an equation for it. If you want that, could be helpful. Yeah, if it's a closed system, then the center mass is just going to keep doing whatever it's doing. So if it was at rest, it'll always be at rest, right? I think I asked you guys that is one of your quiz questions, like they're throwing a snowball back and forth, and the principle was that center mass never changes what it's doing, right? Because all those forces were internal to that system. Rotational dynamics. So here, this is what we did most recently, right? So you guys remember all those? You guys can go back and forth. So, oh yeah, I did get throw an update on the slide. So this very last line I threw on here, since I gave you guys these notes. So kinetic energy, linear, it's 1/2 mv squared, but rotation is 1/2 I omega squared. There's different rotational inertias. You guys have used these recently, right? I think it's basketball. I threw a few times on your quiz. Okay. Oh, what happened here? Okay, I don't know. It's like messed up. 2/5 mr squared for the bowling ball. Parallel axis theorem. I think you should know this, but I've never. I don't think AP actually asked about it, but I think it's good to know. Torque. R cross F equals I times alpha. Same thing. Okay. The cross product just means you care about the perpendicular components. That's like that. You guys could do that. Okay. All right, right hand rule. AP will never ask about that, but might show up in college. Conditions for equilibrium. So the forces go to 0 and the torque goes to 0. That's what it looks like in 2 dimensions and 3 dimensions. Far more likely than not, you'll get that 2-dimensional type question. Okay. 2D equilibrium. Oh, yeah, this guy you should definitely be able to do. Does this look like the bear chasing the goodies? Right, I mean, a little bit different, but basically the same idea. So the forces have to go to 0. In this case, all the vertical forces have to 0 out. but also the torque has to zero out. And it's usually a good idea to pick one as your pivot point, one of your unknown forces, so that you have one less unknown to work with. You can just solve the other unknown. Some version of that. Okay. So force sums to zero, the torque sums to zero. Torque versus time and angular momentum versus time. Now, if you're told a constant torque, right? Say you have a string wound around a disk and you're just pulling it with a constant force, constant raise that give you constant torque, right? What would angular momentum versus time look like? Well, it would be increasing at constant rate, right? Because the slope of that would also represent the torque, which is also constant, right? So that area tells you the accumulated angular momentum, right? Under torque versus time, right? You guys should definitely know these two graphs by heart because you're going to get some questions about these on the AP exam. Like they always ask this. You'll do some version of this. Oh, here's a classic example right here. Here, I just made this new slide recently, but you guys saw this on your quiz recently, right? Right? You guys remember that? You guys got it? That's your quiz answer. Okay. That's a force or some radial distance causes a torque. You do that for some amount of time, causes a change in angular momentum. Boom, boom, just like that. Okay. Angular momentum is conserved. This is your classic ice skater scenario. Right. For a point mass, AP really likes this question. So MVR, right? I think I derived this also recently. Some of you guys' notes, right? So MVR, know that one because that one almost for sure is going to come up on the AP exam. Ball rolling down an incline. Here's what it is in terms of forces. That's how fast the bottom. Here's in terms of energy, which I think is a lot easier to solve. Sorry, some of my slides are. All right, and last slide right here. Roll race. Right, so you guys know that anything on a frictionless incline is going to beat everybody. And then the more rotational inertia it has, the slower it's going to go. Right. Ooh, and that is perfect timing because we are at the end of class. Last slide right there. All right, you guys ready for well, more review? We're going to do more review next few days. Right, you guys have a great rest of your day.